Okay, I think we're live. I am going to now need to post online that we're going. I'm sorry, I got a text. I'm going to post online that we are now having this, and I'm going to set up the link again. I've already posted it once, but to make sure everyone sees it. Hangout happening now. It's happening. Make sure I copy this all the classes. Give me just 1 second, guys. And I think we have a lot of good questions to go through. A lot of you came on. I really appreciate that you put questions in there ahead of time. That is going to help out immensely. All right, and I post this. Okay, let's take a look at our questions. Excellent. Okay. Let me find it. I think there was an easier one I can cover. Okay. The first question I think will be the easiest to answer is from Laura. Is the test for blue classes tomorrow or Wednesday? Tomorrow is Wednesday. The blue classes will not have a test tomorrow. The blue classes will test on Friday. We didn't want you to come back and the first day back from the break have to take a test. So we moved yours to Friday, so we flipped it. So that means Silver Day is going to take the test first on Thursday, and then Blue Day is going to take the test on Friday. So you have another day in there, which is kind of nice for you guys. So that answers that question. All right. Then I will pick Zoe's questions next. Can we go over? And I think we're going to cover this in some of the things, but we'll go ahead and look at it right now. Can we go over the positive and negative characteristics of an equation and the exothermic versus endothermic? Positive and negative. I'm not sure exactly what you mean. I'm going to take a guess at this. So let's go ahead and switch to bamboo paper. And I think this is going to tie into essential skill number 2. I believe, but we'll take a look. All right. So when you say positive and negative characteristics of an equation, I don't know, actually. I don't know what that means. So let's talk about essential skill number 2 and how that'll tie in. And I can, when I hit it again, you have 2 equations you have to deal with. There is the equation, this is 2, let me make this one. Okay, there's the first equation where there's a temperature change. Temperature change. And whenever there's a temperature change, you're dealing with Q is equal to mass times CSP times delta T. Now, if temperature goes up, right, then Q is equal to mass times CSP times, and delta T, by the way, is T final. I shouldn't put it right there. That's going to confuse people. That is T final minus T initial, okay? So T final minus T initial, if temperature goes up, you have a larger number. So let's just say 80 minus a smaller number, 20, because it went up, right? Which is 60, which means that it's positive, which means you added heat to the system. Added heat. Heat was absorbed. It was gained, okay? All that is positive, right? And that's going to give you, that's going to mean your Q is going to be equal to a positive number. Whenever you increase temperature, you have added heat. That means that it's going to be, that means that you have now got a positive for your Q. Positive heat, and that's endothermic. Okay, but if, we'll change to green here, if temperature goes down, okay, and so we've got Q equals mass times CSP times, and now it's 20 minus 80, okay, T final is 20 minus T initial, which was 80, so temperature went down, so now Q is negative, all right? So heat is removed. Heat is lost. Heat is given up. I don't know what else to say. Let's see. Removed, lost, given up. Whatever other words you can think of, right? That's a negative. That's exothermic. So when you're dealing with the specific heat equation, if temperature goes up, it's positive. If temperature goes down, it's negative. All right, that's just for the specific heat equation. Now let's say we're doing, oops. Now we're gonna do phase change. Okay. And now we've got now you're not changing temperature, right? Q equals M times the delta H. And delta H, you can either have delta H of fusion, which is when a solid's involved, or you can have delta H of vaporization when a gas is involved. And so then it's just a matter of, it's straight up, is heat being added or taken away? Okay, so if we said, again, we're back to this. If heat, oh, you know what? Actually, well, they're gonna say this anyhow. They're probably gonna say it. Heat added, heat gained, heat absorbed, okay? And when you do this, you're going from a solid to a liquid, or from a liquid to a gas, okay? Then it's positive. This is endothermic. All right, but switch to green again. If under Q equals M delta H, heat is removed, heat is lost, heat is given up. Okay, in these situations, a gas is going to a liquid is going to a solid. Okay, that means that it is now negative and it's exothermic. It's given up heat. Okay, and we're actually going to come back to this a little bit later because there's something that I'm going to talk about called the lake effect. We didn't talk about this during the unit. I just think it's the coolest thing. It is so cool. Okay, so that's what those are. So hopefully that maybe is a little bit easier for you to identify when we talk about positive or negative characteristics and the exothermic versus the endothermic, because negative is exothermic and positive is endothermic. That's just what it is, okay? Okay, and now that I look at the questions again, we've got a different question. So read positive, negative, what makes a reactions or products positive or negative? Okay, so let me take a look at that. So that answers that question. So Ree's next question. What makes a reactions, reactants, or products positive or negative? I don't know. I don't know what that's in relation to. Products and reactants aren't inherently positive or negative. So I don't know what you're talking about. Actually, I'm sorry. Maybe formulate the question a bit differently and ask it, and then we'll take a look at that when we get there. So now I'm going to look at all the other questions I have, and it looked like a couple people clicked on the what was the purpose of the lab and how are the calculations supposed to be done. So let's do that one next, and I think that will be more than adequate. Okay, so what we're looking at then is, and I'm going to change this to red because it's just so much fun. So the lab question, and the purpose of the lab is to, well, that was the question. What was the question? The question was, you know, what is the CSP? What is the specific heat of an unknown metal? And and let me write that down, unknown metal. And for that, I would have to say that in science, oftentimes you don't know what the answer is going to be. You've got something, you need to figure out what it is. And so that's the purpose of something like this lab, is to show you, hey, you can go through the steps to discover what it is. If you have something unknown, you compare it to something you do know. Like if you look at, like when we look at, we did the flame test, and you had a bunch of colors that you knew, and then you had an unknown, and you looked at the unknown and compared it to what you do know, and then determined that must be what it is. So in this case, let's say you had a substance, and now that we're very limited, we're very early on in chemistry. It's about solving problems. You know, hey, you have this unknown piece of metal. Could you figure out what it is? And this is one way of doing it, through this process. All right. Now, what it's supposed to show you, and the whole thing hinges on one statement. Okay. Heat absorbed equals heat lost, or I think maybe another way we said it, heat gained equals heat lost. Okay. And what that's saying is that, hey, your Q from the heat gained is equal to the Q of whatever it was lost. And when the Q over here, it's gained, it's going to be positive. And the Q over here is going to be negative. They are equal and opposite. Because in a closed system, the heat has nowhere else to go. Okay? So if I have my here's my styrofoam cup. Okay. And we're going to pretend like it's, oops, I am horrible. We don't have to pretend I'm horrible at drawing. We just know that's true. Okay. So here it is. Okay. And there's a lid on it. We're going to make the lid black. Okay. Okay, there's a lid. And it inside is some water. All right. And inside that is our copper tubing. Okay. Now, any heat that's exchanged, right? So there's heat being given off by the copper. Heat's being given off by the copper. It's going to the water. So heat transfer inside the coffee cup, heat transfer is metal to water. Does that make sense? Okay. So metal to water, because it's giving it up. So that means that the Q, the negative Q of heat lost, is equal to the positive Q of its gained. Any water that's going to get heated up is because the metal gave it up. The metal is the one that heated up the water. So they have to be equal. It's the whole thing with the marbles. If the metal had 4 marbles and it gave 2 marbles to the water, so now they have the same amount of marbles, then how many marbles did it lose and how many marbles did the water gain? Well, it gained 2 and it lost 2. It's an equal number, okay? So that's the whole point here. That's what we're really going for. So now there are 2 ways to solve it, right? So this is the why we're doing it. Oh, I'm sorry. Before I get to the solving it, so how did the heat get the metal in the first place? Well, if you remember, I'm going to change this over here. Before here, okay, metal in boiling water. And in that case, the heat transfer went from water to metal. Does that make sense? So in the boiling water, heat went from water to the metal because it heated it up. Then once you took it out of the beaker and put it in the styrofoam cup, it released that metal, it released that heat that it had into the water in the styrofoam cup. So That was all about, at that point, like the only reason we had the beaker in the boiling water is just to get the metal hot. That was all we were trying to do. Heat transfer to the metal, get it hot, get it 100 degrees, then drop it into the styrofoam cup. Then we measure the temperature. That was the only thing you measured, okay? Maybe we'll write that down too. Purple. You measured the delta T. You measured the delta T. And inside of here, okay? And when you did that, you measured the delta T for the water, and then you ended up measuring the delta T for the copper, or the metal, okay? Because the T final minus T initial, and I'll go to the next page for this. The delta T for the water was probably something along the lines of a final, which is like 23.2 degrees Celsius, minus the initial, which was 21 let's say 8 degrees Celsius, okay? And maybe that equals, what does that equal actually? 1.4 degrees Celsius, okay? But the delta T for the metal, oh, horrible handwriting. That looks like a heavy metal band. No, okay. Metal, okay, is equal to final minus initial. It was, whoops. The final was 21.8 degrees Celsius minus the initial, which was 100.0 degrees Celsius. And that was probably equal to 78.2, if I'm doing that right. I might be just winging that. It doesn't, I'm probably wrong. I can't remember, but it doesn't really matter so much. The point is that these numbers are the same, okay? T final minus T initial. T final minus T initial. Oops. I did that wrong, didn't I? Oh, crummy. I'm sorry. T final, which is 23.2. Jeez. It's too bad you guys can't actually talk to me. We need to figure out a way to get some of you into the actual Hangout to correct me when I keep making stupid mistakes. That's no good. Okay, sorry. Let's try it again. These two are the same because the final is the same. There were different initial temperatures, but they ended up at the same. I knew this looked funny when I was crossing it across. Because 23.2 is the final. It's the final for both of them, right? Final for the metal, final for the water. And it's just that on this one, which is now, what is this? 70, oh good Lord, 76 point, this can't be right, 76.8 degrees Celsius, something like that, okay? So the final minus the initial. So it was this huge one, and it was negative for the metal, and it was positive for the H2O, okay? So now that was the only measurement that you took place that was like as far as in the calorimeter. The calorimeter, the only measurement you take is the delta T, the temperature. But you also did the mass of the H2O, which was water inside calorimeter. So, and that was usually about somewhere around the neighborhood of, let's say, 180 grams. And then you had the mass of the metal, which for most of you was about 27.5 grams. And then you also had the CSP of the water, of the H2O, 4.18. Don't forget these units, joules per gram degrees Celsius. You have to know this right here, super important, okay? And then the only thing you don't have is the CSP for the metal, okay? All right, so given all of this information, you can solve it two ways. Since we know that Q positive is equal to Q negative, okay, we know that that's true, we can do it two ways. We can either solve for the positive because we have CSP of the H2O, mass of the H2O, and delta T of the H2O, or we can set the equations equal to each other. So let's say we did the first way, which we're going to solve for the Q of the water, okay? And so let's see, what was that? So that was, which is mass times CSP. Oops, oh, I did that again. Let's try this again. Mass CSP times delta T, okay? So Q of the H2O is equal to, I think we said 180 grams times 4.18 joules over grams degrees Celsius times the delta T of just the water, which was, what was it? 1.4 degrees Celsius, okay? And the grams are gonna cancel out and the degrees Celsius cancel out. And if I do this, where's my calculator? Really quick. I get, let's see, 180 times 4.18 times 1.4, and I get 1,000 Q of the H2O is equal to 1,053.36 joules. Now we're not doing sig figs yet. You don't do sig figs until the very end. Okay, so that's how many joules there. Now, if we want to switch it to, and remember, we said Q of the H2O is positive is equal to the negative Q of the metal. So that means that our Q of the metal has to be equal to negative 1,053.36 joules. And since we're using the same equation, Q equals Q of the metal is equal to M CSP. Oh my goodness, why do I keep writing that capital S? M times CSP times delta T, and we're looking for CSP, so we divide both sides by M delta T. That cancels out. This is M delta T. We're left with CSP is equal to Q over M delta T. So now CSP is equal to negative 1053.36 joules divided by 27.5 grams, and this was 76.8, 76.8 degrees Celsius. And so now you can see none of the units cancel out. It's joules per gram degree Celsius. So our CSP of our, oh, I'm sorry, and this is negative. I almost forgot. That's negative. So the negatives will cancel out. So I divide that number by 27.5 and divided by 76.8. And I end up with a number 0.49, we'll say 9 joules per gram degrees Celsius. Now I just made up those numbers, so that's the CSP we end up with, but that is one way to solve for it. The second way to solve for it is to actually set the equations equal to each other. So we have mass, this is positive because, you know what, let me drop this down. Remember that Q positive, the positive Q is equal to the negative Q, and that this is of the H2O and this is of the metal, which means that mass times CSP time, oh my goodness. It's too bad I don't have good handwriting. Mass times CSP times delta T is equal to negative, remember this is positive, negative mass times CSP times delta T. And you're solving for the mass, or the CSP of the metal. So the CSP of the metal is equal to, because we're going to divide both sides by negative M delta T, negative M. And these are different. This is the delta T of the H2O. This is the delta T of the metal. This is the mass of the metal. This is the mass of the H2O. So you can't cancel them out. So you end up with, let me lower it a little bit more. You end up with, because this is the one you're trying to do right here, the CSP of the metal is equal to mass of the H2O times CSP of H2O times delta T of H2O all over the mass of the metal, negative mass of the metal times delta T of the metal. And obviously the number is going to come out to be the same, but CSP of the metal is equal to, I think I said 180 grams times 4.18 joules over grams degrees Celsius times the delta T, which was 1.4 degrees Celsius, divided by the mass of the metal, so that's negative 27.5 grams times, and it was negative 76.8, I think, degrees Celsius. So the negatives will cancel out. These degrees Celsius cancels out. The grams cancel out. I'll just make these positive because they cancel out. So you're left with joules per gram degree Celsius, and your CSP ends up being the same thing, which is 0.499 joules per gram degree Celsius. You can solve it either way because heat gained is equal to heat lost, except for that when it's lost, you have to have it make it negative, okay? So that's an example of how you would solve all that and how you would talk about it. At least I hope that's how you would talk about it. Should that, I mean, however you come across that, however we end up doing that, okay? So that's the lab question. Hopefully you got a lot out of that. And of course, I'll be open to more questions on that. Okay, another question. Oh, we got it from Sori. Thank you very much. Checking that out. Laura has another question. Can you please explain when to use the 3-part step process for combining phase change and heat problems? I would be delighted. I have a couple things to show you for that. Okay, so I need to open up one of my documents. I have something in here. I think I have something in here. I do. Where did I put it? I apologize. I have several documents that I'm working off of at the moment, trying to make sure that you see them all. Here we go. Okay, let me try it now. I'm going to share a picture with you. Okay, so here's this picture. And in that picture, you can see that there are different times to use equations, okay? Actually, let me show you another picture real quick. Okay. Oh, I can't just, can I just shift to G? Oh, it did. Oh, sweet. Okay, I wasn't sure, it just switched over for you. Okay, so you can see that this is water. It's solid at the bottom, then it's a liquid in the middle, and then it's a gas at the top. And it, as heat energy, moving right across the axis, you're adding heat energy, and the temperature goes up that direction. So as you add heat energy and you're moving to the right, temperature is going up until you get to, this is 0 degrees Celsius. Now it starts melting and it goes into a liquid, and then the liquid warms up, and then it gets to 100, and then it starts boiling until all of the liquid becomes a gas, and then it starts heating up again. Okay, and going the opposite direction as you're removing energy, right? As you're removing energy, this exothermic going to the left, it's endothermic going to the right, exothermic to the left, it condenses, right? It goes from a gas to a liquid, that's condensation. And then once it's all from the gas, it's become a liquid, then it starts cooling down some more, okay? And then it gets down to 0, and now all that liquid water has to become a solid before it can start cooling down again. So you can see that's what's happening at each of these stages. Now, if I go back to the original picture, this is what the equations you use at each one. When you are increasing temperature, when temperature is changing, you have to use the Q equals MCAT. Q equals mass times CSP, that's the C, CSP, times delta T. Whenever temperature changes, that's when you use that. When there is a phase change, meaning that there's no temperature change, but you are continuing to add or remove energy, then this axis should not be time. That axis should be, I'm sorry, I didn't pay attention to that. That axis should be heat. I pulled this off the internet. Can't always trust that, my apologies. But you're gonna be adding heat. And so as you add heat, it's a positive M delta H. Well, the delta H is positive going to the right. If you move to the left, delta H becomes negative. Whenever you have a gas involved, if it's going to a gas, Going from a liquid to a gas, that's vaporization. It's going from a gas to a liquid, it's still vaporization because a gas is involved. If you're down here, a solid to a liquid, fusion's involved. Liquid to solid, fusion's still involved because a solid is involved, okay? That's how you determine which ones to use. So let's do an example problem. What we just looked at. I think Laura would like actually to see a question. Let me switch to my bamboo paper. Okay. Whoops, where'd my bamboo paper go? It's on the screen, but I've hidden it among layers and layers of window. There it is. There you are. Okay. So let's go over here and let me change the ink to blue. So what's going to happen is that you have something that says, we'll use an equation. Let me write this up. I'll just write it up first. Okay, so when you look at this, you're gonna be like, hey, there's a temperature change. That means that it's a specific heat problem. I know it's specific heat. And yes, it is specific heat, okay? But if you were to draw a little flow chart of how you're supposed to process these problems, if you have water and it crosses one of the critical temperatures, 0 degrees Celsius or 100 degrees Celsius, then that means it's going to be a 3-step. Okay, 0 degrees Celsius or 100 degrees Celsius is a 3-step. Well, this one goes from 125 to 75, and it's steam, so it's H2O, it's water. It's going to be a 3-step problem. That's how you know. You have to look at it whenever you see temperature change. So temperature change, if water, you have to look for one of the 2 critical temperatures. If it crosses a critical temperature, then you've got a 3-step problem, okay? And 2 of the steps are specific heat, okay? So you know that step 1 and step 3 are both gonna be the Q equals M times CSP times delta T. And they have to be different because the CSPs are different. It depends on the 2 phases, right? And so we'll give you the list. We'll say, hey, what are we gonna say? CSP for ice is gonna be, oh, don't hold me to this. Oh, you know, why don't I just look it up on the notes instead of saying something wrong and irritating myself and you guys. Okay. Okay, there it is. Okay. So the CSP for ice is 2.03 joules per gram degrees Celsius. Oops, that was a weird one. And then the CSP for water, liquid water, is equal to 4.18. You guys should have that memorized by now, joules per gram degrees Celsius. And the CSP for steam is equal to 1.97 joules over gram degrees Celsius, okay? So we'll give you that. Then we'll also give you the delta H of fusion of water, which is 334 joules per gram. Don't forget those units. And we'll give you the delta H of vaporization for water, which is 2259 joules per gram. Okay, so we've given you all this information, and you now have to figure out, oh, and in step 2, of course, this is all going to come from when you have a phase change, Q equals M times delta H. And you have to look, okay, if I'm crossing 100, it's delta H of vaporization because a gas is involved. If it's crossing 0 degrees Celsius, it's fusion because a solid's involved. So delta H of vaporization. So I'm going to solve this problem really quick, or I'm going to write it out. I think I need to keep moving to make sure I cover everything. So step one is a Q equals M CSP delta T. And this is always true for a three-step. It's always true for a three-step. The first and third ones are the specific heat equations, and the second one is the phase change. We're doing this for steam. We're doing this for steam. So Q is equal to the mass. Oh, did I say what the mass was? Cooling steam. Oh, well, you know, we're just going to say, oops, we're going to say it's 10.0 grams because that's what we're doing. Okay, 10.0 grams. Sorry about that. The mass, 10.0 grams, times the CSP for steam, which is 1.97 joules per gram degrees Celsius, and the delta T, which is the final, which is 100 degrees Celsius, minus the initial, which was 125 degrees Celsius, which is going to end up being a negative 25 degrees Celsius. That's key, okay? So Q number one, when I plug this in my calculator, 10 times 1.97 times 25, negative 25, gives me negative 492.5, and the Celsius cancel, and the grams cancel, leaving me with joules, so it's joules. Okay, that's step one. Step two will always be Q equals M delta H, which is a pretty easy one. Delta H, we said at vaporization. So that's equal to 10.0 grams times 2 gram. The grams will cancel out, leaving me with a Q. So this is Q1. I should have written, this is Q2. Q2 is equal to 22,590 joules. Did I do that right? It's times 10. Why am I doubting my ability to multiply? Yeah, that's it. So obviously that's a lot of energy. Oh, and it's negative. It's negative. It's negative because heat's being lost, right? It's going from a vapor phase to a liquid phase. So that's negative, all right? And the last one is another temperature change one. Q equals, this is Q3, is M CSP delta T, and this one's for water. So that means that it's equal to 10, or let me give myself some more space. So Q3 is equal to 10.0 grams times the CSP of water, which is 4.18 joules per gram degrees Celsius, times the delta T, which is the final 75.0 degrees Celsius, minus the initial, which is 100, because it all happened at 100 degrees Celsius. So that's going to be a negative 25 degrees Celsius. So my Q3 is equal to 10 times 4.18 times negative 25. And Q3 is equal to, whoops, did it again, is equal to negative 1,045 grams cancel, degrees Celsius cancel, oops, right there, leaving with joules, okay? And then my Q total, what we want to know for the whole equation is Q1 plus Q2 plus Q3, which is equal to negative 4, you know, I'm not going to have enough room. So I'm doing the other page. Of course, I'm not going to remember it. So Q total equals to negative 492.555 joules plus negative 22,590 joules plus negative 1,045 joules. Did I make them all negative on the other page? I sure hope so. Yes. Okay. And when I add those all together, negative. I believe that if I did my calculator right, oops. You guys with me? Yes. Okay. That I believe the final answer is negative 24,487.5 joules. Now we do sig figs. I go back to the original problem and my measured's 10.0, 125, 75, 75. I should have put 75.0, but let's just pretend like it's just 2 sig figs, then I'm fine with that. So if it's 2 sig figs, I'm just to here, 24. I don't do any of the rounding. My answer is negative 24,000 joules, okay? Which is pretty huge. So what's the major contributor to that? When you have all the Q, what's the major contributor? It is Q2, which is the phase change. That's the major, it's the major contributor here to the amount of energy lost, right? This is exothermic because it lost energy. So that's how you do a 3-step problem. So hopefully that makes sense. That's a good question. There's only like 1 or 2 of those on the test. Okay, so now let's cover the essential skills that we haven't covered or talked about yet. Essential skill number 1. I actually want to show you guys something. Let me see if I can find it. There's a little video, an animation. So I'm gonna try to put it on. I'm gonna try to put it on here. Where is my YouTube app? There it is. Okay.
If the 2 samples come in contact, a transfer of than those of the same substance with a lower temperature.
Okay. Okay, so I'm hoping that came through okay with the YouTube video. Basically, oops, I'm doing this. Essential skill number 1. You see that so higher temperature equals more motion, or vice versa. Okay, that's basically what we're saying. We're saying that, oh hey, did you can you recognize that a higher temperature, there's more motion, there's more molecular motion. It's all about the molecules. We need to really spend a lot of time on molecules. You need to think about it in regards to the molecules for a lot of this stuff. There's more molecular motion at a higher temperature, and a lower temperature has less. Okay, so let me take a look at something. Okay, so if I asked you, we use the same one with like 125 degrees Celsius H2O versus 75 degrees Celsius H2O. Okay, which one's moving faster? Where are the molecules moving faster? H2O at 125 or 75? Right. I feel like Blue's Clues. Yes, you're right. I can't hear anybody talk. They're faster at 125 degrees because it's a higher temperature, okay? And the second part of that one is that heat moves. This was a mistake from earlier. Heat moves from a higher concentration to a lower concentration. I say concentration, but just areas of high heat and then move to areas of low heat. So for example, when you have the, here we have the beaker. Oops, no. Let's do, make this green underneath. Here's the hot plate. Okay, hot plate underneath. And it's boiling. Okay, and then you drop in the copper. Okay, in this example, where's the heat moving from and to? Where's the transfer? And you would say H2O to metal. Okay, and this is the metal. Okay, because the water is boiling, it's transferring its energy to the metal. Then, when we talk about moving, now we've got a styrofoam cup. Okay, and you've got the water inside of there, and you put your metal copper in there. Okay, so now it moved from, we use purple to it went from here into here. Okay, and this was 100 degree, so 100 degree water, and this was 20 degree water. Okay, so now what's the heat transfer? Well, now it's going from the metal to the H2O because the metal is obviously hotter coming out of the beaker coming into there. Okay. Okay. So that's essential skill number 1. I think that's pretty straightforward. Let's move on to essential skill number 2. And this is the one that keeps tripping everybody up. Essential skill number 2. Let's look in the notes. Where do I have the notes? There we go. Okay. So here's the notes. Page 3, the note right here. Okay. Let me open this up a little bit so I can see it better. Okay. So as looking at this graph first, ice to water to steam. As it increases, it goes through positive delta H of fusion. There's melting, gets to water. It's boiling, vaporization, goes to steam, coming back the other direction. And it's all positive going to the right. Going to the left, it's going negative. Steam condenses into water. Delta H is negative vaporization there. Water freezes into ice, and that is also delta H is negative. And so what does that mean? That means that here, we're going to ask you questions like going from a solid to a liquid. Is it breaking bonds or is it forming bonds? Well, if you are adding energy and it's going from think of the states of matter dance, it's locked together, right? To go to the point where they have to actually be able to start rolling over one another, they're going to have to break apart, okay? And then to go to a gas, and they really have to break apart, right? They have to go far apart. That's what's going to have to happen going from a liquid to a gas. And then forming bonds, they become slower and slower. They're going to start forming bonds. Going from a gas to a liquid, they're forming bonds. And going from a liquid to ice, they're forming bonds, okay? So I'm actually going to show you guys an example of this. And I'm going to give you guys a second to look at it and see if you can figure out the answers to these, okay? So there's number 2 there, A, B, C, D, and E. So go ahead and take a look at them for a second. So the question is, can you solve each one? This is an example of what like the correctives are going to be. So in the first one, you have this equation, and then here's delta H. Well, check it out. You don't even really care about the equation because the delta H tells you everything you need to know. It's negative 251. If it's negative, it's exothermic. Okay? Straight up. And then in the second one, you have another equation, you could care less about because they give you delta H. So is that exothermic or endothermic? Well, it's positive, so it's endothermic. So then you have to look down here. Okay, well, endothermic is not an option. Heat released or heat absorbed. Well, if it's endothermic, heat absorbed, heat added, heat gained, that's all the same. So heat absorbed is the right answer. Solid carbon dioxide, dry ice, changing to a gas. You've got a solid going to a gas. That's a huge jump. How do you go from a solid where it's all locked in to a gas that's running all over the place? Are those bonds broken or made? Well, clearly they are broken. To go from something that's solid and locked down and fixed in place to something that's scattering all over whatever container it's in, filling up the volume of that container, it has to be broken. D, condensation on the outside of a glass of water. So you have to remember, I know some people are struggling with what is condensation. Condensation is going from a gas to a liquid. Condensation is what you see the dew in the morning. It was so cold that the air in the water that was a gas became a liquid because they removed all the heat out of the air. That's what's happening. When you get close to the glass, the warm air is getting close to the cold glass and it's losing its heat. So then the vapor in the air becomes a liquid. And that means that if it's losing heat, if it's moving left, right, on that graph, it's moving left on that graph, it is exothermic. It is losing heat. That's condensation is exothermic. It's negative. That's the one right there. That question right there is what gets everybody 90% of the time. You gotta remember, condensation, negative. Condensation, exothermic. Condensation, forming bonds. You should just get that one down. And then finally, E, boiling water to form steam. Is delta H a positive value or negative value? If you're boiling and you are, in order to get the water to form a gas, you have to add a bunch of heat, right? You have to add a whole bunch of heat on your stove. So that means delta H has to be positive. The answer is that it's a positive value, okay? So hopefully that helps you a little bit with that one. But I think that's all of that on essential number 2. This would be a great time to talk about, let me go back to my bamboo paper. I think that people also struggle with the idea of, sorry, just give me one moment. I get this stuff moved around. I don't even know where my bamboo paper, there it is, okay. Oops. Okay. Okay. There's something called the lake effect. Okay. So if you lived in the far north, you would know about this, and it's fine you don't. But, or you guys might know about it, I don't know. So there's a lake. Now the water is freezing. So as it's freezing, you have a liquid going to a solid. Okay. And if you look at the graph, okay, that means that you have this liquid right here, and this is the solid. It is going this direction. It's going from a liquid to a solid, which means that it's, and remember, your graph here, heat is on the bottom and temperature is on the side over here. That means it's losing heat. If it's losing heat, where is the heat going? The heat is actually coming up out of the lake. It's actually, as it's freezing, it's releasing heat into the air. And in the north, they oftentimes will build fishing houses on the lake. Well, since the water's freezing, it's actually releasing a little bit of heat. So it's actually warmer on the lake than you would imagine. It is giving off heat. It is the coolest thing. So just something to remember. Maybe that might help you remember that if you're going from a liquid to a solid, as it's freezing, it is giving off heat. Not a lot all the time. It's not like it's gonna, like, obviously when you're in the freezer we've artificially refrigerated, we've frozen, we put in something that will help lower the temperature, so we're not going to melt our own ice as we're making more ice, but that is something that does happen. Okay, let's do essential skill number 3. Essential skill number 3 is the phase change, and we've talked a lot about this already. So I wasn't planning on spending a ton of time on this, but I can give you one problem. Let's see, do I still have my, where is it? There it is. Okay. I can give you a sample problem really quick because it's getting to the end. I'm not going to be on here too long. Here's a sample problem. So for number 3, I will tell you that delta H of fusion is equal to 334 joules per gram. And delta H, and the thing is, these are going to pop up on the test, and it's not going to say, oh, by the way, this is essential skill number 3. So you're going to have to really pay attention. 2259 joules per gram. And how much heat is released when 25.4 grams of water freezes to ice. Okay, and there are a few things that will help you identify what the correct thing is to do here. The first is the fact that, let me change the color here. Let's change it to something a little bit green. Okay, released, right there. Heat is released. That means that your delta H is going to be negative, okay? And you've got another key here. You've got water going to ice. So this is a liquid going to a solid, which means that when you have liquid and a solid, you are dealing with the delta H of fusion. Okay, so there's some keys in the wording that will help you. So you're looking for, and it's looking for Q. Q, how much heat is released, and then right here, this is the mass. So they're pretty straightforward. So Q is equal to M times delta H of fusion, and it's negative. So Q is equal to 25.4 grams times delta H of fusion, which is negative. For this one, it's negative 334 joules per grams, and you know the grams are going to cancel out. So your final answer is 25.4 times negative 334 is Q is equal to negative 8,000. Oops, wow. I was not paying attention when I wrote that one down. Negative 8483.6. And we look at sig figs, and the only measurement in here, this is going to determine our sig figs 3. 1, 2, 3. The 3 becomes a 0. So Q, our final answer, is negative 8,480 joules. Oops, not a very good box. So that's how you solve for essential skill number 3. And finally, let's do essential skill number 4. Okay, essential skill number 4. I'm going to change the font color. Essential skill number 4 is specific heat. That's this, and so you know you have to do with this whenever there's a temperature change. You're going to recognize it when there's a temperature change. So let's give a practice problem. Okay. All right. So the CSP. Let's see. Here, the specific heat. Specific heat of iron is 0.450 joules per gram degrees Celsius. And the rest of this is how much energy must be added, oh, what a pain, that's okay, added to a 56.3 gram sample to raise the temperature from 25.0 degrees Celsius to 58.0 degrees Celsius. Okay. All right. So let's look at the things that are giveaways. Specific heat, right there. You know you're going to use the specific heat equation. They give you the specific heat of iron. How much energy you're looking for Q must be added to a 56.3 grams. So there's your mass. 25 to 58, there's your delta T, and it's going to be positive. So, and how much is it at right there? There's another thing that tells you it's going to be positive. So you've got Q equals M times C. Oh my Lord, I cannot do that right the first time. M times CSP times delta T. So the mass was 56.3 grams. The CSP, 0.450 joules per gram degrees Celsius. And the delta T was 58.0 minus 25.0 degrees Celsius. Okay, so I plug all that in. That's pretty straightforward. 56.3 times 0.45 times the difference of 58 minus 25, and I get 836.055, and the units, grams cancel out, degrees Celsius cancel out, leaving us with joules, sig figs. We don't look at the specific heat because that's a constant. That's not a measurement, so we don't look at that. The measurements are 56.3, 25.0, and 58.0, so it's 3 sig figs. 1, 2, 3, so my answer is actually positive 836 joules. Okay, and that's essential skill number 4. Sweet. All right. Now, if you're continuing to watch, I wouldn't necessarily call these Easter eggs, but we'll just say these are bonuses now. Bonuses at the end. There's going to be a question where they're going to ask you for what is the specific heat. So, which is like the lab. So you're going to have to rework that equation. So you're given this, you're not actually given this, you need to remember this. Q equals CSP times M times CSP times delta T. So then you're actually going to end up with CSP is equal to Q over M delta T. Anytime you have to rework the specific heat equation, Q always ends up on top of the opposite. So that's that one. If you do the other ones, you know, for example, M is equal to Q over C. Sometimes I really irritate myself. Q over CSP delta T, or delta T is equal to Q over CSP M. And you know what they're going to ask you? They're going to ask you actually for a T2, a T final. They're going to say, what's the final temperature? Final temp. What is that one? So you can do it 2 ways. If you do it that way, you can solve for delta T. Delta T is equal to Q over M times CSP, and then delta T is equal to T final minus T initial, and you have the delta T, and usually you're given the T initial, so you're going to end up with T final equals delta T plus, because you have to add it to both sides, right? To cancel it out, because it was T final minus T initial. So you have T final equals delta T plus T initial. So you can do it that way, or you can say that since delta T is T final minus T initial, you could say that T final minus T initial, right, is equal to Q over M times C. I have issues. We all have issues, right? Okay. So then what you're going to end up doing is T final is equal to Q over M times CSP plus, that's all together, plus TI. Okay? So you should be aware of those problems. I don't know if there's one like that on the study guide, but you should know how to do that. Okay. Other bonus things you should remember. Remember, hot pad or a oven mitt versus metal pan, which has the highest specific heat, which has the lowest specific heat. And to do those right, you should know why, right? Which do you guys think it is? Oops, I need to finish this out over here. The highest specific heat, remember, it's the energy required to raise 1 gram by 1 degree Celsius. So does it take a lot of energy to raise 1 gram by a degree Celsius, or does it take just a little bit? A high CSP would take a lot of energy. So the highest is the oven mitt. The lowest is the metal pan, right? Because it doesn't take much energy at all to make it hot. It takes very little, which is the energy required to raise 1 gram by 1 degree Celsius. Is it easy? Low CSP. We're gonna rename these just for fun. We're gonna rename them. Oops, no, I don't want to do orange. Orange is too close to red. Let's do green. Easy to heat. That's low CSP. High CSP is hard to heat. That's what those really should be called. Highest is hard. Lowest is easy. Okay, if you have a low bar to get over, it's easy to get over the bar. If you have a high bar, it's hard to get over. So high CSP, oven mitt. Low CSP, easy to heat. Okay, something else you need to be aware of. Another bonus Easter egg. Remember the pot of boiling water? Versus the Pacific Ocean. Okay, which has more heat. Okay, and that would be the Pacific Ocean because it has more molecules. At this point, I'm going to show you another really, really cool video. I think I've only told one class about this video. Where is it? There it is. Okay. Give me just 2 seconds. I just moved it wrong. Okay. Here we go. Oh, wait, that's not it. Oh, because I need to copy the little Bill Nye. Hey. I know you guys like that, right? Who doesn't like Bill Nye? Oops. Okay. Clearly, I have not mastered the YouTube. It's really cool. Trust me. Bill Nye talks about stuff. Anyways, let's skip that right now. That was a lot of wasted time. So let's see if there's anything else I can remember about the test. Oh, I got another little bonus piece. A bonus piece would be, and we probably haven't really talked very much about this, which is okay, but I believe it's in your notes, is the capital C calorie versus the lower C calorie. Let's go ahead and take a look at your notes. I think that would really help. This is one of those things that you've got to pay attention to what's going on. Where is it? I don't know. Is it in here actually? Did we take it out? Maybe we took it out. Well, that's not very much fun. Well, we'll see. Anyways, the point being, let me go back. All these things. These bonuses don't sound so neat very much when I'm taking so long to show them. The nutritionist changed the calories because really a capital C calorie, one capital C calorie is 1,000 of the small calories. So if you're eating something like, oh, look, this little thing is only 75 calories. Really, what they're saying is that's 75,000 calories. But nutritionists are like, people are never going to want to say, oh, yeah, I don't mind eating 75,000 calories. So they're going to make a new, it's like a kilocalorie, okay? A capital C calorie is the same thing as a kilocalorie. So it's like 1 kilocalorie is equal to 1,000 calories. Kind of interesting a little bit. All right, I'm done with the bonus ones. The bonus ones are wearing me out. Obviously, you should do that. Oh, you should also, though, one last thing. I cannot emphasize this enough. I don't know why students don't take a greater advantage of this. I want to show you the ScienceGeek.net, okay? I just don't think I can emphasize it enough in here. You go to chemistry, you go to review, and it gives you these things to choose from. So you look at them and you scroll down, and we are in the middle of the Thermo Unit. So if you look into second semester, I believe, here, thermochemistry concepts and calculations of specific heat and latent heat. Latent heat is enthalpy. Latent heat and enthalpy are the same thing. Energy diagram practice, reaction energy, thermochemistry and energy diagrams. Those are all great things you can look at. Let's look what's thermo, show all questions. Okay, the specific heat of aluminum is 0.90 joules per gram degree Celsius. How much energy is required to raise the temperature of 10 grams of aluminum from 10 to 20? So basically, you've got Q equals M CSP delta T. M, 10, CSP, 0.9, delta T, 10 to 20, which is 10 degrees. So 10 times 10 is 100. 100 times 0.9 makes it, I believe, 90. So I go down here, 90 joules. And I get the smiley face. Yay for us! We got it right. Okay. And then you can do other questions. Okay. 1 of 22. I'm not sure where the other questions are. Oh, there they are. Okay. So you can go through each of the questions and do the same thing. I just can't emphasize it enough. I think it's great. I think the stuff he does, this teacher, Mr. Allen, out of Visalia, El Diamante High School, he does a great job. Let's see, is there anything else? I don't know. Calculation of specific heat. I mean, there's just specific heat problems. If you guys want practice, there it is. That's perfect for you guys. Okay. All right, that's enough for now. I'm worn out. I hope you guys have a good night. Get some sleep. The test is not tomorrow, but the next day. or the next Thursday and Friday. So let's hit the ground running and really make this worth it. Make it so that this isn't your lowest test grade. Make it so that this will be a good one, so you can you're not worried about your grade for the rest of the semester. Okay. All right. If you have questions, please come and see me or your peer teacher. All right. Thanks a lot, guys. And I am out of here. Bye.